All right, physics reaction video number 25. Today it looks like it's going to be about Ohm's law and Joule's law. So we'll get started here. I guess I need to hit play.
And power equation practice page. We're just going to take it step by step. This page is basically practice in manipulating equations, and we definitely have struggled with that this semester, and so we need to practice for sure. Okay, so
So I don't know if you saw the 10% battery warning and didn't even cause a hitch in her voice. She's with there and boop, said, okay, whatever, I can deal with it. And you can see it up here. Honestly, this is stressful for me to watch. So I'm curious to see if it all comes apart. But it was great how it didn't, she had only just started. And so she absolutely could have said, oh, fine, I'll fix that first. I'll hit pause. I'll go find my charger and then I'll start again. But she clearly has some confidence that she's going to get this done. This whole video is 7 minutes long. So she must know that she has, I don't know, 10 minutes of power left. Can't tell what kind of machine this would be. It's possible this is an iPad. I guess I don't know for sure. So right away, you heard her talking about some scaffolding here, and really trying to help students work through the combinations of things that need to get done. So cool. Let's keep going.
First off, for letter A, it says write Ohm's law. So we know from the notes that you have hopefully already looked at today that Ohm's law is I equals V over R. Okay.
Wow, that's so interesting, right? So Ohm's law is the combination of V, I, and R, the linear combination, right? And so often it's discussed as V equals to IR, but I equals V over R is, completely consistent with that. What's interesting about I equals V over R, I actually think that that might be the construction that helps the most. Why? Because usually in the lab, you have known voltages and known resistors. And the thing you got to go measure is the current, right? So it's actually rare to have easy access to things with a constant current, or a known current and an unknown other stuff. Now, we can do homework problems, right? You can do that all you want in a homework problem. But it's really interesting that the way she's laying this out immediately for the students is I equals V over R.
And then before we move on, let's actually take just a minute to think through other ways that we could write this. Okay, so let's say that we were going to solve for R. Well, we know from lots of practice that when you know what we think of as the answer and you need to know what's on the bottom of the equation, we just switch places, right? So we'll put the R there and put V over I. And
Cool.
That's another way to write this equation. Okay. And then a third way, let's say that we want to solve for V. Okay. Well, if we want to get V here by itself, we're going to multiply by R to get R off the bottom, right? And so V is going to equal I times R.
Cool.
So all three of those equations are just different ways to write Ohm's law. And we're just using algebra.
I've said this before, and by no means would this be the example that I remember from my students, but there's all kinds of things like this where the three different ways you could write this are three different ways you might use it in homework problems or exam problems. And I remember I was really debating with some students one time when they were trying to craft a potential equation sheet for the next day's exam. And a student nominated in the analogy, the student nominated this one. And I said, oh yeah, great. If you want that one, I think what I was doing at the time is they got 10 or some fixed number of equations. And we were debating on the prep day, like what should be the 10 equations. And somebody said, oh, for sure, this one. And everyone nodded their heads. But then, a smaller minority of students sort of said, oh, and this one and this one. And it was so interesting, right? Because it was this commentary on knowing themselves in the heat of an exam, not wanting to have to do algebra and just be able to churn through. And, of course, it was a vibrant debate in the classroom. They're like, oh my gosh, there's so many other things we need on that equation sheet. So, but when you think about it, right, you don't want algebra to be the stumbling block for students. We want physics to be, well, we don't want any stumbling blocks, but we want our students' brain at the physics part. And if it helps to really lay all three of these out, then go for it. What do you know? What don't you know? And all of these are saying the same thing, right? Grab any one. So if you grab this one, it's basically saying, if you have access to how much voltage is across a thing and how much current is flowing through it, you can have a real good sense of what the resistance is. Because if you increase the voltage, the resistance will go up, and if you increase the current, the resistance will go down. Why is that? Well, let's take the current. If the current can go up for the same voltage, it means it's easier to sort of squeeze electrons through that sucker, so the resistance goes down.
Algebra rules to rearrange and manipulate the equation. Okay, next one is asking you to write Joule's law. I don't think our notes actually refer to this as Joule's law, but it's just the power equation. So P equals I times V is the format in the notes. We're going to rearrange it just like we did a moment ago with the other equation here. And so let's solve for I first. Okay, so if we want I by itself, let me get a different color. If we want I by itself,
I'm just going
to
fast forward
divide
here.
by V. Let's
I'm fast forwarding because I'm curious about part C.
Then we would divide both. And so algebra questions, just exactly what they're asking for. C says rewrite Joule's law.
Yeah, this is the one I'm interested in.
Okay, so Joule's law was the power equation. So let's start with what we know. Okay, we know that P is equal to I times V. Well, we're going to leave a blank space for the I right now because we're not supposed to use it, but we can go ahead and fill in the V. Okay, and then we're going to look up ahead and see, well, what did I equal? Well, if you look up at the Ohm's law equation, I was equal to V over R. So let's just drop that in right here. We'll say
Love
V
it.
over R.
Yeah, that was cool.
Okay. And then we can clean that up a little bit. We make it look a little bit prettier and say that since both V's were on the top, we could say V squared and then put that over R. Either equation is right, so if you leave it as V over R times V, that's totally fine. If you simplify it and say V squared over R, also totally fine. Okay? All right.
And what she's building up to here is really thinking about C and D, right? C and D are super useful equations. She's about to do I squared R for power, doing the same trick, and I'm excited to see how she grabs stuff from part A. But start thinking about R, right? And say, oh, well, this what she has right now. If this is the first one you show them, students see, okay, wow, So if I want lower energy losses from the power plant, okay, I guess I need really, really large resistances, right? Because R is sitting here in the denominator. And we think about, oh boy, if the power plant is trying to get energy to our house, we don't want to lose very much in the wires, and wires have resistance. We don't want to lose too much in the wires getting to our house. And so this right away is like, oh, okay, well, R's in the denominator, so we should make R big, but we'll come back to it here.
Right, and then the next one says rewrite Joule's law without using V. So we're going to start with what we know again. We've got P equals I, but this time we can't use V. So let's look up ahead again. Let's look at Ohm's law, and we see V is equal to I times R. So let's plug in. Cool. We're going to drop in I times R there.
Cool.
From here. Okay.
So she didn't draw the arrow that time. I thought she might.
And then we can clean that up a little bit and say P is equal to I squared, because it was I times R. Again, either way of writing it is totally fine. Okay.
So here, just to finish the power line analogy, right? Here you're like, oh, okay, well, boy, before this stuff, if the power plant is sending energy my way, then I want a really, really small resistance. Well, notice how those two sort of disagree. Like, oh, I want a huge resistance to make this small. No, I want a really, really small resistance to make this small, right? These are the really, really exciting things to work with students. What I love about what she's doing, and I think I might just stop here, but she's obviously going to do this, what she called a flower, right? Like, let's get every possible construction together so that as we start to deal with real life situations or homework problems, we know, okay, boy, what are we trying to figure out? What are we being asked? And to understand that Ohm's law and what she's calling Joules law together usually sort of can figure all of that stuff out. And as you go and tackle complex circuits, you're able to figure out the current, the voltage, the resistance, and the power for every single element, which is kind of what we're up to usually in these homework problems. So if you feel like your students are decent at algebra, you wouldn't need to do this. You basically only need two things. You just need this one or one of these, and you're good to go, right? But so often we run into students who are like, no idea, don't know how to do it, right? And so to really show them this, oh, that's cool, right? Kind of like the kinematics equations when you get, I don't know what the initial velocity is, or I don't know what the time is, or I don't know what the distance is. And there's so many different ways to monkey with it. So I think showing students this stuff can be super, super useful so that you can get them thinking about the physics, which I think is really, really great. I was going to say one other thing, something about having two equations. It's escaped me. So I think that it would be interesting to find out whether you have any students checking out, right? So, oh, yeah, of course. But then again, I remember I was a pretty fast sort of algebra type student when I was a student, but I was also one of those students who wanted to do everything, like, oh, yep. And I would like finish this notes before my teacher could say it. And it's just sort of helping me be proud of my algebra skills, right? So I don't see a big problem there. I think that now they're equipped, they can go on. Oh, I know what I was going to say. I think that doing this work, going from A and B to C and D, actually assessing the student's ability to do it can be useful because they might have now, let's say it's a couple weeks from now, they're doing an exam or something, and they've been churning out homework problems using these two equations. I think it's totally legit to sort of say, hey, where did these come from? What's going on? And students would have to say, oh, well, actually, you just put it together with these guys. And that question about power lines is so fascinating, right? Because if you make them sort of one-dimensional mistake I was making, we're really only focusing on one element, this R, right? You're like, gosh, I don't understand. Should R be big or small? But really, it's these combinations like, okay, hang on a second. What exactly is the power plant supplying? Well, it's a fixed voltage or it's a fixed current. Oh, hang on a second. We have to adjust. I think that that's really, really interesting. It's fascinating, by the way, in case you've never really thought about it, this one tends to dominate. This kind of approach tends to dominate. So, it's subtle, right? There's some interesting nuance to that. But this kind of work can really help your students tackle that. So great job. All right, everybody, have a great day. And remember, physics teachers are awesome.